Hello, this is Mason Haggerty with question 9.25 from the Fundamentals of Heat and Mass Transfer, 8th edition. So, in this question, we're looking at a central receiver concept of a solar power plant. Many heliostats are at ground level and are used to deposit or direct a concentrated solar flux to the receiver, so CubeSun, which is positioned at the top of a tower. However, even with absorption of all the solar flux by the outer surface of the receiver, losses due to free convection and radiation reduce the collective efficiency below the maximum possible value of 100%. So we're considering a cylindrical receiver of diameter 7 meters and length 12 meters and emissivity of 0.2. So here's the diagram given. Again, you can see the heliostats directing the sun towards this tower. So for part A, we're saying that if all of the solar flux is absorbed by the receiver and a surface temperature of 800 Kelvin is maintained, what is the rate of heat loss from the receiver? The ambient air is quiescent, so not moving at a temperature of 300 Kelvin, and irradiation from the surroundings may be neglected. If the corresponding value of the solar flux is Qs equals 10 to the 5th watts per meter squared, what is the collector efficiency? So up here, I have tabulated useful values. So we have diameter, length, the surface area calculated as 84 pi m squared. And we're just looking at the outside surface because it seems to focus on that. So we're neglecting the top. The emissivity is 0.2. And gravity will be 9.81 meters per second squared. So assumptions. We're assuming steady state. We're neglecting the environment radiation, so radiation to the tower from the environment. And we were treating the cylinder as a vertical plate, so if that is for the free convection. And we're assuming air is an ideal gas. So to begin our analysis, we know that Q sun equals 10 to the 5th watts per meter squared. The surface temperature is 800 Kelvin. T infinity is 300 Kelvin. We're saying that all Q sun is absorbed, therefore Qs is equal to 84 times 10 to the 5th pi watts, which is equal to 26,389 kilowatts. So first we're going to look at radiation just because it's easier. We know that radiation is, the E is equal to emissivity times the E of a black body, which is equal to emissivity Stefan-Boltzmann constant times surface temperature to the 4th. We have all of these values. The emissivity is 0.2. The Stefan-Boltzmann constant is known at 5.67 times 10 to the negative 8 watt per meter squared Kelvin to the 4th, multiplied by the surface temperature of 800 Kelvin to the 4th. From this, we find that per meter squared, there's 4,645 watts lost. So we multiply this by the surface area of the receiver, and we are losing 1,225.75 kilowatts to radiation to the environment. So next we'll be looking at convection, and for convection we'll be using the Nusselt number for a flat plate. So for a flat plate, there's two possible options. We can either use equation 9.26 or 9.27. 9.27 is slightly more accurate, and it is 0.68 plus 0.67 times the Rayleigh numbers to the 1/2, all over 1 plus 0.49 over 492 over Prandtl number, all to the 9/16th, all to the 4/9. But you can only use this if the Rayleigh number is below 10 to the 9th. The other option, equation 9.26, can be used more generally, but it is slightly less accurate, and that is 0.825 plus 0.387 times the Rayleigh number to the 1/6 over 1 plus 0.492 over Prandtl number to the 9/16th, all to the 8/27th, all squared. So, obviously, we now have to find the Rayleigh number, which is equal to the Grashof number times the Prandtl number, which is equal to G beta times Ts minus T infinity times the L's cubed over V alpha. So for this, I've pulled in the table A4 for air at 550 Kelvin. The reason we use 550 Kelvin is because that is the middle point between the surface temperature and the ambient temperature. So when you average the surface temperature of 800 Kelvin and the bulk temperature of 300 Kelvin, you get 550 Kelvin. So looking at the table, we pull out our useful numbers, which are the Prandtl number, V, K, and alpha. So that's your kinematic viscosity. Your K is the watts per meter Kelvin, and alpha. So you get that V is equal to 45.57 times 10 to the negative 6 meters squared per second. K, you're going to have 43.9 times 10 to the negative 3 watt per meter Kelvin. Alpha equals 66.7 times 10 to the negative 6 meters squared per second. And Prandtl number is equal to 0.683, which is also equal to just V over alpha. So, back to the Rayleigh number. We can plug in all of our values. So we have 9.81 meters per second squared. That's gravity. Beta is actually just equal to, can be approximated as 1 over the temperature in this case. And so we get 1 over 550 Kelvin. Multiply that by the 800 Kelvin surface temperature minus 300 Kelvin bulk temperature, multiplied by the L, which is, in this case, for the flat plate, that is the height, which, again, is L in this equation, all cubed. And then that is over 45.57 times 10 to the negative 6 meters squared per second times 66.7 times 10 to the negative 6 meters squared per second. And this gives us a Rayleigh number of 5.07 times 10 to the 12th, which is significantly greater than 10 to the 9th, so we have to use equation 9.26. But now that we know that, we can plug in all the values. We have that the Nusselt number is equal to 0.825 plus 0.387 multiplied by the Rayleigh number, which we just found, 5.07 times 10 to the 12th to the power of 1/6, over 1 plus 0.492 over the Prandtl number, which again from the table is 0.683 to the power of 9/16, all to the power of 8/27, all to the power of 2. This equals 1,868. So from this, we know that H is equal to Nusselt number times K over L, the characteristic length. So we have Nusselt number as 1,868 multiplied by 43.9 times 10 to the negative 3 over 12 equals 6.835. And so from this, we know that the heat loss to convection is H times the surface area times the delta T. That gives us 6.835 watts per meter squared Kelvin multiplied by the surface area, 84 pi meters squared, multiplied by the delta T, which is 800 minus 300 Kelvin, and that gives us a loss of 901.9 kilowatts. So again, just a reminder, the Q sun is equal to 26,389 kilowatts, and our losses are equal to the Q rad and Q convection, which is 1,225.75 plus 901.9. So losses are 2,127.6. So then you subtract that out from the Q sun, divide that by the original Q sun, and find your losses. And this gets us an efficiency of 91.9%. So that's it for part A. And then for part B, it asks the surface temperature of the receiver is affected by design and operating conditions within the power plant over the range from 600 to 1000 Kelvin. Plot the variation of the convection, radiation, and total heat rates as a function of TS. For a fixed value of Q sun equals 10 to the 5th watt per meter squared, plot the corresponding variation of the receiver efficiency. So for this, I created a MATLAB script. As you can see here, I first define my variables. We have the emissivity equals 0.2. We have the Stefan-Boltzmann constant is equal to 5.67 times 10 to the negative 8th. The surface area equals 84 pi. Gravity is 9.81. Your L is 12. The Q sun equals 10 to the 5th multiplied by the surface area. Your surface area, I created a vector ranging from 600 to 1,000 with an increment of 0.1 Kelvin. That's pretty arbitrary. You can set it to whatever you want, but I figured that would give enough resolution. The bulk temperature will be 300 for all cases. And then I just transposed the Ts plus T infinity over 2, which is the average temperature. So that's where you pull from the tables. I just transposed it because I prefer working in a different form on MATLAB. So then you have to tabulate all of the You pull out all the table values for the range that we're working with. So you're pulling out 300 Kelvin, 350 Kelvin, 400 Kelvin, 450 Kelvin, 500 Kelvin, 550 Kelvin, 600 Kelvin, and 650 Kelvin. And then you have to pull the corresponding values for V, K, and alpha, which I just call A here. And so as you can see here, you get 4 different vectors that correspond with the given table values, and then you can use the MATLAB function interp1, where you feed in a x vector and then your value vector and then the new x vector that you plan to interpolate to, and it will provide an output that is the interpolation at all the points associated with the new x from the original x and y values. So that gives you your new V, K, and A that you'll actually be using. And then I created a for loop which basically just runs through every temperature increment, and it finds the Prandtl number by using the V over A at that point. It finds the Rayleigh number by using the equation used in the analysis above, and the Nusselt number, again, exactly as above, but you're just running through it at each temperature increment, and that also gives us the H. So now that I had the H, you run through the new for loop, where it goes through each convection loss based on the different H's. The surface area is constant, and the TS will change, again, as the original TS changed, minus T infinity, which is constant, and you have the loss of radiation, which is just the constant emissivity times the constant surface area times the Stefan-Boltzmann constant times all your various surface temperatures to the fourth. And you then total these, and your efficiency is 100 times the Q sun minus Q total over Q sun. And then this is just graphing code. And here's your output. So you can see that I have 4 different graphs. I have the Q of radiation, the Q of convection, the Q total, and then at the bottom there, the efficiency of the with losses. And as you can see right there at the middle at 800 Kelvin, I plotted out the original values that I calculated by hand up above, and you can see that it aligns with the model, so we can assume that it works. And so that's the graphs you get, and you can see that as the surface temperature increases, the efficiency drops because the radiation and convection will both increase losses. So thank you very much.